So what actually happens is that gravity forms a temperature gradient in the troposphere of a planet. The sun's radiation can warm up parts of that troposphere, especially in the upper regions where it's colder and the radiation is actually strong enough to raise the temperature. And then, because of the gravitationally induced temperature gradient, it is possible for heat transfers to occur in such a way that they're more or less flowing up that sloping thermal plane, getting down to the lower troposphere and eventually into the surface. And when we introduce water vapour, the temperature gradient is reduced. This is well known, although the reasons that they give are not really correct. It's not actually due to the release of latent heat, it's due to intermolecular radiation, which has a temperature levelling effect which works against that gravitationally induced temperature gradient. And that's where we get a situation where, in fact, dry regions are warmer. They have higher maximums and higher minimums, just slightly higher minimums. And you can see that in that study, which was based on 15 tropical locations, inland locations, throughout 3 different continents in the tropical regions there, based in the hottest month of the year when the sun was almost directly overhead, so we don't have to adjust for the angle of the sun. And that's the sort of result that we get when we compare places at effectively similar latitudes and similar altitudes. There are actually some adjustments for the altitude there to make them all the temperature that they would have been if the altitude had been around 600 metres. And you can read about that study at the back of the paper there, and it's also in the book Why It's Not Carbon Dioxide After All. Now, just recapping a little bit on the first video, this process of what we call heat creep is based on the fact that the temperature gradient is a state of thermodynamic equilibrium. Now, you need to think of that rather like a lake, the surface of a lake. When rain falls on one side of a lake, for example, a new storm just makes the level a tiny bit higher on one side of a lake, then that new water will be spread by gravity over the whole of the surface. When the rain stops, it will eventually come back to a new equilibrium situation. Now you have to try to imagine this plot here turned on its side so that the green strip there, which represents the sum of gravitational potential energy and kinetic energy at a molecular level, that strip will be horizontal because that's the equilibrium situation. And so it's just like new rainwater falling on a lake, and it spreads out. And that little red triangle indicates the new rain, and basically then when we move down to the next page, we find an example of what happens then as that red spreads out, and you'll see that some of it is effectively going uphill, going up the temperature gradient. And this is the reality of things, and this is what, of course, the climatologists have never had the initiative to imagine what's happening, because people get very much committed to this concept that heat only goes from hot to cold, and that, strictly speaking, is what we call the Clausius statement of the second law, but it's really just a corollary of the overall second law. The main second law is about entropy increasing to a maximum, and entropy includes, or should include, the gravitational potential energy. The problem is, and you can look it up in Wikipedia under thermodynamic potentials, you can see that they, in most situations, they ignore gravity. It says so there very specifically. And that's because in most cases we're talking about laboratory type experiments and everything's basically at the same altitude, and we're looking at a situation which is basically in a horizontal plane. So yes, in a horizontal cylinder of gas, warm air at one end will effectively lead to there eventually being a uniform temperature along that cylinder. And this is all due to molecular collisions. The molecules don't actually travel the whole length of the cylinder or the whole distance from the top to the bottom of the atmosphere. They pass on their kinetic energy like a relay race. Effectively, they bang into or collide with other molecules, and because they've got a bit more energy, that energy is then shared, and they both come out with a more equal distribution of energy in the long run anyway. On a macro scale, we do find that the mean kinetic energy, which represents the temperature, evens out. And if you can imagine one layer of molecules at one level and another layer just below them, separated by perhaps something like the mean free path, which is only maybe 80 or 90 nanometres, very small distance, but nevertheless, we can imagine that the average kinetic energy at the top level is a little bit lower than the average kinetic energy at the lower level, where it's warmer. And balancing that out is a difference in the gravitational potential energy. And this is exactly what happens when a ball falls, for example. It's got a certain amount of potential energy, and as it falls, it loses some of that potential energy and gains kinetic energy. And likewise with the molecules, as they move between collisions, gravity will act on their mass and accelerate them just a little bit more. And when they come down to the lower level, they will have kinetic energy that effectively matches the existing kinetic energy, the higher level of kinetic energy at the lower level, and vice versa. When they go upwards, they will slow down a tiny little bit, and their kinetic energy will match that at the higher level. Now, I know there's a distribution, but on a macro scale, where we're considering at least a billionth of a gram or something of that sort of nature, statistically it evens out, and we do have a mean kinetic energy which represents the temperature. So if you can understand that, that's broadly why the temperature gradient is a state of thermodynamic equilibrium or maximum entropy. Nothing will change. The molecules are just moving up and down between different levels, and when they get to the other level, they already have kinetic energy which matches those that are already there, so they don't cause any more change. It's just the same as if you had a horizontal cylinder of gas, sealed cylinder, and up one end you originally had warmer gas or air. Eventually everything will even out on a statistical basis because of the collisions. And so when it is all even, then nothing more happens. There's no more heat transfer on a macro scale, because when the molecules collide, they're colliding with others that have, on average, the same amount of kinetic energy. But when you turn it into a vertical column, you've got this phenomenon where the kinetic energy increases as it goes down, or decreases as the molecules go up, or if there's any component in their motion, upward or downward. And that means that effectively, if they are going to have the same kinetic energy when they get to the different level, there will in fact be a temperature gradient. They will have gained kinetic energy coming down at the expense of potential energy, and vice versa going upwards. Now, this principle has actually been used in a centrifuge machine, which is referred to in this diagram here. And there's an experiment that's been written up there that basically creates very, very low temperatures as a result of bringing these molecules, guiding these molecules into the centre of a centrifuge, and as they're doing so, they're gaining potential energy relative to that radial centrifugal force field, and they get down to temperatures of just 1 K. Now, when we talk about K temperatures, we're talking about Celsius temperatures, the centigrade temperatures, minus about 273, and 0 K is absolute zero. You can't get anything colder. Well, they've got them down to 1 K, just minus 272 C. And that just demonstrates how a force field acts on molecules and effectively creates a temperature gradient along the radius, so the ones at the outside are much hotter. The same sort of thing happens in a vortex tube, and you can read about that on Wikipedia, and that's the common thing. Now let's just go back a bit and talk about what the climatologists talk about in terms of radiation and energy budgets. Here we see a diagram, an original diagram constructed by NASA, and it just shows net energy, basically. And this is really what is actually happening. But there's a big but to this. You'll notice that the amount of incoming solar energy is reduced to about 51% by the time it gets down to the surface. And in other energy diagrams, you'll see that they calculate a figure of the order of 168 watts per square metre of solar radiation striking Earth's surface on average. That's a mean figure, of course, an average figure. Well, what does that boil down to? It means that, in fact, the solar radiation is not enough to raise the temperature of the Earth to the observed temperatures that we see. And that's somewhat staggering, because we stand in the sun and we think, oh, we're getting warmed. But in fact, a lot of the warmth that is going into the land and the ocean and everything is coming from this process that we call heat creep, whereby the energy moves down by this sort of process. Okay. There's a thing called the Stefan Boltzmann law, which tells us to what temperature radiation would raise what they call a black body to if the radiation is at a certain level. And that 168 watts per metre squared would only raise such a black body to a very cold minus 40 degrees centigrade. So what's going on here? The mean solar radiation is not able to explain the mean or average temperature that we see. And you might say, oh, but it's a lot hotter at the equator and things like that. Well, it's not that much hotter. Places like Singapore don't get above 32 degrees, even when it's the full blast of the sun and the hottest days of the year. And that's about the limit of what the sun could do anywhere on the surface. When you get hotter days, it's because there's been a build-up of thermal energy, not so much due to the radiation of the sun that's actually striking the surface, but because the atmosphere above has been warmed, and this heat creep process has brought energy down, and so it's warmed up the air above a dry desert, for example, and that indeed can build up in temperature if the atmosphere itself is getting warmer in the colder regions where the sun can actually do it. So you need to imagine this lake that we had before, where there's a heavy storm on one side of the lake and it's building up the whole level of the lake, and eventually the shoreline on the other side of the lake rises, and that's the sort of thing that is happening effectively with the surface temperature of the Earth. Now, the fascinating thing is that this process continues on down into the crust and the mantle and even to the core. And we can confirm this, so we can confirm that it happens on other planets also, because we can actually calculate what the temperature gradient ought to be based on the fact that we've got potential energy and kinetic energy changing. And when we work out how much potential energy we lose, and we treat that as being converted to kinetic energy, we find that we get a certain temperature rise, and from that we can work out what the actual temperature gradient, or as they call it, the lapse rate, would be. And it's based, if there was no radiation, it would be based on the acceleration due to gravity divided by the average specific heat of the gases in the atmosphere. Now, this formula works in all planetary tropospheres. We can apply it to the 350 kilometre high nominal troposphere on Uranus, and we find that the actual temperature gradient is around 90 to 95% or so of that calculated value. And it applies on Venus too, but there it may be closer to 70 to 80% or so of the gradient, and that's because there's more carbon dioxide up there radiating and effectively cooling the surface, because it's reducing the temperature gradient in the same way that water vapour does on Earth. Water vapour on Earth reduces it from about 9.8 centigrade degrees per kilometre down to even as low as around 6 or so, but rarely more than that. So this actually happens on all planets, and it happens in the outer crust of Earth. We can see a temperature gradient there, but it does not mean that there's a flow of heat coming out of the Earth all the time. Again, it's an equilibrium situation, and in fact, common sense tells us that when the sun does effectively warm some areas on a warm, clear, sunny day in the tropics, and perhaps does raise the temperature to 32 degrees in Singapore, that some of that energy is going underground. But when it does go underground, it may well be going to warmer regions. if you go down 10 kilometres, and they've done this sort of thing with borehole measurements, in Germany they got down to about 9 kilometres, and I believe there's another one somewhere that went to about 12 kilometres, and they find that the temperatures are up around 300 degrees centigrade or so at those kind of depths. And there is a temperature gradient that's, roughly of the order of 25 degrees per kilometre under the crust. But if we work it all out with the specific heats involved and all that sort of thing, we find that we're getting much the same sort of process happening as we do in the troposphere. And we can extrapolate that when we get to the mantle. We find that the specific heat reduces a lot because, sorry, I should have said it increases a lot, because of the temperature there, and that means that the temperature gradient reduces because that specific heat is in the denominator, and also the force of gravity effectively reduces as you approach the centre of the Earth because you've got mass above you and a mass below you that are sort of working against each other. So that's why the temperature gradient in the mantle might come down to only about 1 degree or so per kilometre, far less than in the outer crust. So we certainly don't have a uniform kind of conduction gradient from the core to the surface. But what is fascinating about all this is that effectively it is the sun's heat that is effectively supporting these temperatures underground in the mantle and even down to the core. So planets are not still cooling off, and Uranus is a good example of that because we find that there's no convincing evidence of any net loss of energy of any significance at the top of the Uranus atmosphere. And that brings me to the consideration of what they sometimes say in these energy budgets and so on, and is that carbon dioxide is trapping heat, and therefore it's all building up and that sort of thing. Well, one thing they do is measure the incoming radiation at the top of the troposphere there, and likewise the outgoing radiation, but the actual measurements have got an error in them that could be 0.5% or so. And then they take the difference and they try to tell us that, there's a 0.3% warming effect, trapping effect or whatever, but in actual practice they could be out that measurement, and at other times anyway they show a net loss. And if you think back to 1998, we showed you in the first video there that the temperatures were actually higher in 1998 than they are now. So there must have been a net loss of energy at the top of atmosphere over that whole period. And all this is natural, and that's what it all comes down to. Natural cycles that are explained there on the website. If you have a look at them, they could well be due to planetary orbits affecting things like the cosmic ray intensity, which could affect cloud formation. The magnetic fields from the planets reach to the sun, they could affect the intensity of the sun, or various things that we perhaps don't yet understand. But there certainly does seem to be a correlation between the sunspot activity and the long-term cyclic trend that's got a period of about 1,000 years, 900 or so years, that goes back not only to the medieval warming period, but back to the Roman warming period or so, 1,000 or so years before that. So these long-term natural cycles are very evident, and there is a superimposed 60-year cycle, and some say there's some other cycles as well. It's really quite complicated, but that's not all that surprising when you consider there's several planets up there having some effect in various ways. And one, for example, is the fact that the gravity of Jupiter actually affects the eccentricity of Earth's orbit. So sometimes Earth's orbit is pretty circular, and other times it's more elliptical, and that varies over a cycle of about 100,000 years. And because of that, it means that the mean annual distance of the Sun from the Earth varies, and that therefore varies the intensity of the Sun, and that could well be an explanation for the glacial periods. Some call them ice ages, but really they're glacial periods that are separated by around about that same sort of period of 100,000 years. So, in a nutshell, it is all natural. Water vapour reduces the temperature gradient, and that leads to cooler surface temperatures, and that in itself blows apart the whole greenhouse conjecture, because they talk about water vapour warming the surface by 30 odd degrees, and if carbon dioxide increases, supposedly water vapour gets higher and warms it more with a feedback sort of mechanism, and it's just simply all completely wrong. So talk to your friends about these videos and pass it on, and read the website climate-change-theory.com, and go to the evidence page there. Down the bottom of there you'll see the papers linked. I've got another paper on radiated energy written back in 2012. Read these things and pass the word around, and hopefully within a few years the truth will come out.